All right, let's dive in. Today we're going to tackle one of the most mind-bending ideas in all of physics, the fact that time isn't constant. But we're going to look at it through a totally fresh and kind of weird new lens that involves, of all things, whirlpools. Let's see how the spin of the universe can actually change how we think about time itself. But first, let me ask you this. Why on earth does the GPS on your phone, something you probably use every single day, depend on a theory that Albert Einstein dreamed up more than 100 years ago? Well, the answer is a lot stranger and way more important than you might think. And that answer starts with one of the wildest predictions in all of science. This idea that time isn't some universal metronome, ticking away at the same speed for everybody, everywhere. It just doesn't work that way. This is the absolute core of Einstein's special relativity. The big idea is that your journey through space and your journey through time are completely tangled together. So if you hit the accelerator and speed up your movement through space, you're forced to slow down your movement through time. I know, it sounds like something straight out of a movie, but it's a fundamental rule of our reality. Now, physicists have a name for this, for your personal experience of time. They call it proper time. Think of it as the time that's ticking away on your watch, right here, right now. It's the time you feel. And as we're seeing, your proper time can tick by at a totally different rate than someone else's. And this brings us right back to your phone. See, those GPS satellites are absolutely whipping around the Earth at almost 4 kilometers a second. At that crazy speed, their clocks literally tick slower than ours do down here on the ground. And if we didn't correct for this time dilation, the errors would pile up so fast that within 24 hours, your GPS would think you're miles away from where you actually are. Okay, so we've established time dilation is a real thing, and it's all about speed. But what if there was a completely different way to look at it? A recent paper suggests something fascinating. What if we could describe this cosmic law using the physics of spinning fluids? Now, what's so cool about this is the author's goal. They're not trying to rewrite physics or anything. Instead, they're building a kind of bridge, a new way for us to understand an old, tricky idea by linking Einstein's universe with the world of, stuff that spins. And to build that bridge, we need this one key idea from fluid mechanics. It's called circulation. Simply put, it's just a number that tells you how much swirl is happening in a fluid. So if you stir your coffee, the circulation is just a way to measure the total spinning motion you've just created in that cup. So wait, how in the world can the swirl in a cup of coffee have anything to do with time slowing down near a black hole? Well, believe it or not, this is the core insight of the paper, and the connection is actually surprisingly direct. And this is where the magic happens. Think of it like a new recipe for time. Step 1 is the classic formula from Einstein. It all depends on velocity, v. Step 2 is the link from fluid dynamics. It turns out that in any spinning system, you can describe that exact same velocity using its swirl, or circulation. So for step 3, you just swap out the velocity part of Einstein's formula for the swirl version. And just like that, you get a whole new equation for time dilation that's based on rotational flow, not straight line speed. And this is the most important part. This doesn't change the physics at all. The amount that time slows down is exactly the same. But what it gives us is a totally new way to think about it. We've just reframed the whole question. Instead of asking how fast is it going, we can now ask how much is it spinning? But hold on, there's a really crucial piece of the puzzle we have to talk about. This new swirl perspective is awesome, but it's really important to know that it only describes one of the two ways that time can get all twisted up. You see, time dilation actually happens for two different reasons. The first is what we've been talking about, the kinematic effect. It's all about motion, and that's the part our new circulation formula is great for. But there's a second one, the gravitational effect. This comes from Einstein's other theory, general relativity, which says that time itself actually runs slower when gravity is stronger. Our fluid analogy doesn't really capture that second part. And for something like a GPS satellite, you absolutely have to deal with both. Its incredible speed slows its clock down, but being further away from Earth in weaker gravity actually speeds it back up a little. The final correction is a mix of the two. So this fluid perspective gives us this really neat new way to visualize and calculate that first piece of the puzzle, the slowdown that comes purely from motion. Okay, so let's bring this all back down to Earth. How big are these effects really, and why does thinking about them in a new way even matter? Take a look at this number. Just look at it. That is the time dilation factor for a person standing on the Earth's equator. just from the planet spinning. It is an impossibly tiny number, but what does it actually mean in the real world?
Well, what it means is that every single day, a clock at the equator, which is spinning really fast, will lose about 8.6 microseconds compared to a clock sitting perfectly still at the North Pole. We're talking about millions of a second. You would never, ever notice it, but it's real, it's measurable, and it's happening constantly.
Now, let's put that into perspective. Look at this comparison. If we say the time dilation effect from the Earth's spin is our baseline, we'll call it 1. Well, the effect on a GPS satellite, just from its orbital speed, is about 100 times greater. And that is why these tiny, weird effects from relativity are absolutely essential for the technology you use every day. So, let's wrap this up. We started with this fundamental truth: time is relative. We then learned that we can describe this effect not just using speed, but with the language of fluids, with swirl or circulation. It doesn't change the outcome, but it gives us a powerful new mental model, a fresh tool to really get a handle on the complex dance between time and motion in our universe.
And that really just leaves us with one final big question. What this paper really shows us is the power of looking at an old problem from a completely new angle. That's how science moves forward. It makes you wonder, right? What other huge cosmic mysteries could we solve? What secrets are just hiding in plain sight, waiting for us to stop looking at them as just particles and waves and start seeing them as part of a grand cosmic fluid?